This lesson is looking at vibrations and haptic feedback. So in other words, whenever you have something vibrating, whether that's a game controller or your phone when you tap it, or newer computers, instead of having physical buttons under the trackpad, they might vibrate instead. This is all looking at those ideas. So, whoops, went the wrong way. Haptic feedback. So haptic feedback is giving vibrations to, I'll use this word lightly, mimic the feel of pressing a button. So if you tap your phone screen, or if you tap a touch screen, you're not pushing anything in, there's no mechanics there, there's nothing that's going to click. Whereas if you think about pressing down a key or pressing a button like on a game controller or a Game Boy or something, when you press a button, there's feedback, like you can feel that it gets harder to push, and when you get to the bottom, you feel that it stops. So you know that you've pushed that button. If you touch a touch screen, though, you don't know necessarily by feel that you've done that. So one thing that, as we've designed consumer devices, we found is really useful to give some sort of feedback so that you know that that button press was registered. That idea is haptic feedback. And as we've gotten better and better at designing vibrations and engineering and all of that stuff, we can make it feel closer and closer to you actually pressing a button. And so that's the goal, is that you could eventually have something that feels like you physically pressed a button, or you've got that nice kind of click sensation to let you know that yes, you did in fact, like the phone or the laptop or the tablet did register that result. So all the technology we're going to talk about here can be used to give that sensation. They can also be used just to vibrate, to let you know that someone's calling or something like that. So before we get into those technologies, we need to talk briefly about an electric motor. So what an electric motor is it's basically a coil of wires, which we're quite familiar with coils of wires by now. And that coil of wire will come out and attach to something that we call brushes. And it's just a fancy way of saying a way that you can attach something to it without, it's a way to attach something to this coil of wire without actually attaching and getting twisted up. So then you've got another object over here that will touch those two coils. And then as this piece over here spins, this wire, this top wire, will go along this upper piece of metal, then it will disconnect and then go around the lower piece of metal and repeat and go around like that. This is another thing that I can kind of physically make a model and show you in class. But the idea is, if there's a magnet on this piece right here, I think I've drawn this slightly wrong. The magnet should actually be, yeah, this should actually have the magnet and the coil over here. And then this is just connected into a power source. But basically what can happen is you can create the current in this wire, you can get it to spin because of the magnetic field, and then when it switches to the other set of wires, it will reverse the electric current, and it will cause the magnetic field to switch and cause a different vibration. This is getting a bit into the technical physics, but the idea is you can create a spinning motion by constantly switching back and forth between which direction the electric current is running, and that will switch the magnetic field constantly, which will cause a magnet to spin. And if that magnet is attached to like an axle or something, that axle can spin. So if that kind of went over your head, the main thing to track is switching the current will allow for a magnet to spin. So if I run the current one way, then run it the other, and I just keep switching it back and forth, and I've got a magnet nearby, that will cause the magnet to spin. Then we can just attach something to the magnet, and that will create your motor, because you just plug something in, start it spinning, and it'll go. And just like with before, we can put the magnet on either part. We can have the magnet sit still and the coil of wire spin, or we can have the coil of wire sit still and have the magnet spin. It doesn't matter. The point is, using these electromagnetic properties, we can create spinning. That's useful for creating kind of the classic vibration motor, which is the eccentric rotating mass. And what you have here is you'll have your motor, and then on the end of the motor, you'll have like a half cylinder here. And then as that rotates around, because it's lopsided, right, it's only half of a cylinder, it's going to kind of throw the motor to the left and to the right, just like if you have a washing machine that's not loaded up properly, or a drying machine that's not loaded up properly, and you hear like suddenly it starts going ka-chunk, 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 ka-chunk as the whole thing shakes. Same idea here, but we're intentionally trying to get it to do that by only putting it on half. So if we looked at from the front, you'd have the motor in the back, you'd have the rod or the axle sticking up, and then we'd have like half of a cylinder. And then when this rotates around, when it flings to the other side, it kind of throws the whole motor's going to kind of feel thrown to the left. When it comes back around, the whole motor kind of feels thrown to the right. And if you spin this really fast, it ends up just kind of being thrown left and right and vibrating back and forth. This is your classic motor. It's the ones that if you hear the vibrator quite loud, like the vibration motor quite loud in your phone, it's probably an eccentric rotating mass. This is what phones and like video game controllers have typically used. So if you open up an old controller with vibration in it, you can see you'll be able to find like a little motor that's got a little chunk of metal on the end that's not a complete circle. And just when you want the controller to vibrate, you turn that motor on and it causes it to shake back and forth. A newer technology that we have is a linear resonant actuator. And this is newer technology. It actually works like a speaker. And if you have an Apple device and you've heard of their Haptic engine, it's just a fancy Apple name for a linear resonant actuator. And the way that this works is you've got instead of having a motor, you've got a coil of wire with a magnet in it. And then that coil of wire you've got this all in an enclosure. That coil of wire is connected to, whatever you want to activate. And then next to the magnet, you've got a spring to like one side or the other of the enclosure. And then, as we've talked about before, if you run a current through a coil of wire, you create a magnetic field, and that will push or pull the magnet. And it works exactly like a speaker. But instead of wanting to create sound, we just want to create the motion. So this won't vibrate as quickly as a speaker will, but if it vibrates slower, it'll just cause you to feel that vibration or feel that kind of back and forth. Linear resonant actuators are great because they use less energy and they create less sound. So the rotation ones, you'll typically hear kind of the buzzing or like the whirring because it's spinning around. It has to spin it really fast to get the kind of vibration you want. The linear resonant actuators don't have to use as much energy, and they create less sound because they're just kind of jostling back and forth. They don't have to move as quickly. They won't create as much of that kind of buzzing or humming sound. So as time goes on, we'll probably see a lot more of these used in technology, but for the time being, it's a little more expensive. We haven't kind of worked out all of the kind of ways to make it small and scaled really well. It's still a little bit finicky of a technology to produce. But that's how vibration works. That's how kind of the two main technologies and why we use it.